I will begin with a word of prayer. So, dear Father, we thank you for today. Again, Lord, I thank you for your students. I just pray that you to help us to use this time wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so you guys had homework questions. I'll get to them then. Which one? 2.9, number 57?
2.9, number 9.
Number 9. So we have K, a normal subgroup of G, right? And what else do we know? The order of little g is equal to n. G is in G. Well, good to know. All right. What else do we get there? We're supposed to show that the order of kg in gk and g by k, g mod k, the factor group g by k, divides n. This is number 9 of section 2.9 in Nicholson. Okay. Let's see here. Yeah, so I guess I would look at, what is kg to the n power? Right, it's kg to the n, which is k, right, times 1, which is k, like you said, which is the 1 in the factor group, right? But a factor group is a group, right? So what theorem do we have? What does this say about the order of, what does this say about the order of kg? It has n as a multiple, right? Sometimes my brain only will work in multiples. At the moment, it's one of those times. In fact, most of these meetings that we have here, I'm not really that wise. Is that enough? Right. If kg has n as a multiple, that means that n divides kg, right? Divides the order of kg, yeah. It was kind of uneventful. It's okay. It looks scarier than it is. Other questions?
We can do 2.9 number 4.
I am not averse to answering homework questions in 2.10 if you want. So it's like you don't have to rule that out. So 2.9 number what?
4. I think it's like the example that
Oh, interesting. You guys got to keep me honest here. I'm worried about my logic in this kind of problem at this kind of time. Well, that's generally true. So you got G is formed from the direct product of these cyclic groups generated by A and B respective, where the order of A is 8 and the order of B is 12. And we're supposed to look at, what are we looking at here? K is the cyclic subgroup of the direct product generated by a squared comma b cubed. All right. We're supposed to find the, you're right, this is kind of that example. That's not a, you're exactly right. This is like a way worse version of my example 5 from the section that I didn't cover in class. A to the fourth. Can I go back to example 5? Goodness gracious. That's part A. And part B, maybe these should be numbered 1 and 2 here. So here, K equal to A comma B squared. Find the order. Order, order. Order of K, the right coset A squared B. Ng by K, where K is not the same as part A. All right, so there's the problem. Is there a C? Phew, okay, all right. I mean, this may just be a raw calculation. So let's just, let's work on it. Is this relevant? I mean, it's kind of, this is number 9, that's number 4, but I wonder if it's helpful. But it's kind of asking the same ballpark of question. All right. Let's see here. How to start. This is, I'm not sure it's entirely necessary, but it might be helpful for me just to go ahead and, that may be fool's errand. How big is this group? It's got 96 elements. Yeah. And how big are these subgroups? So what's the order? What's the order of a squared b cubed? Maybe I should start by asking that. I don't know if that's directly what I don't know.
4. Yeah, 4 for that one.
Order is 4. How do you know that?
If you did 4.
Oh, just direct calculation?
Yeah.
Well, okay, 4 is the first time that can be 1. And that, when you raise it to the 4th power, is 1 again. So I guess, okay, so but by direct calculation you got, it's what also? What did you say? LCM?
No, I was thinking, never mind.
Yeah. But I agree with you that has order 4, because by direct calculation it has order 4. How about the other one? That one, I think, has order 6. I mean, we have various theorems that rule out some of the possibilities and so forth, but oh, curses.
So it's either
But it's not 8.
or 6. Well, I think
So that
48.
why isn't it 8?
I believe.
Squared to the 8 is
So the thing, we're not thinking about this clearly, right? This has order what? 8. This has order what? So what's the least common multiple? 8 and 12 is what? Is what? Oh yes, that's what I wanted you guys to tell me. Thank you. Oh, you guys just said it. You didn't think it. All right. You got me. So it looks like 24. All right. But that you can do the same over here, right? What is order is this? Order what? A squared has order 4. B cubed has order.
That's what I was thinking when I said LCM. I just didn't really realize what it was LCM of.
It's the LCM of the orders of the elements. And the order of the element is not the order of the element to a power, is the thing, necessarily. I mean, it could be, but only if we happen to hit, a power which is relatively prime to the order of the element which is given. Okay, so apparently K is a subgroup of order 4, and in part B, K is a subgroup of order 24, right? Which means writing out the cosets, the K cosets for part A, is kind of a drag. There are 24 of them. How many K cosets for part B? 4, not so bad. Okay, now I don't know if that really helps. I'm not committing us to doing anything explicit like that. I'm just trying to get my mind around the problem, okay? So let's see, what next? What are we supposed to do? We're supposed to calculate the order. So I'm looking at K. I want to look at, I think it's just direct calculation, guys. So K a to the 4th B, right? And what happens if we square that? So, what it is, of course, is K a to the 4th B squared, right? I mean, so really what we should focus on here is probably just the representatives as to avoid writing a bunch of stuff. So like that, what's that one? That's a to the 8, b to the 4th, right? A to the 4th b squared cubed is what?
Would not be squared if I do switch to b squared. Just a to the
Oh, heh. Sorry. Wait a minute. Which problem am I on? That was B. It's worse than that, guys. Oh, no, it's not. Focus. Focus. Right here. All right. So it was this was what I was working on. A to the 4th B, A to the 4th B. There. Oh. Good grief. This is the harbinger of things to come. Okay, I think I got it on my system. All right, I think you can start to see what's going on here, right? Dot, 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 dot. Eventually you get A to the 4th B to the what? 12, right? A to the 4 times 12, which is 64? No, 4 times 12 is 48. What's wrong with me? Good grief. 48, b to the 12th, yeah? The point is, it could not have been, well, wait a minute, do I have to, but then I'm forgetting the rules of the game. What are the rules of the game? I'm trying to find the order of this coset, right? So I should work mod k. I'm not even thinking about mod k at the moment. I'm thinking just plain old in the group G, right? So let me think about this for a second here. What's the order of A is what? The order of A to the 4th is what? It's 2. What's the least common multiple of 2 and 12? 12, right? So I'm just calculating that the order of this element in G has order 12. Well, duh, we knew that. But that's not even what I need, is it? I need to take advantage of the fact that, anytime we have KK, we get K again, right? So,
Oh, we need something
Yeah, I mean, we don't have to wait till we get back to 1, 1. It suffices to get back to something that's in K again, yeah.
So would Q, would it be order 3?
Is that in K?
Yeah.
Yes.
Yeah, that is
That's in K? How is that in K?
Oh, wait, never mind. Sorry.
So would you start with K then, and then multiply it by a fourth b successively, or just multiply it once and square that?
What I'm trying to say is, fine, if you like, I can write it out. I mean, K, 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 K. But I just was trying not to write the Ks, sorry. Which is bad because I'm not communicating to you guys what I'm thinking. And I'm not even thinking it myself, as you can see by the fact I wrote it all the way out to 12. Right? Now, this just says what? The order of, if this has order n, then
The order has to
divide
It
n.
only has to go like,
So we only have to look at divisors of 12.
wait, why 12?
Is that 7?
This is G, right? Oh, I'm sorry. This right here is the quote-unquote G, right? If we think about problem 9, since we've got it on the board. So we really only need to check divisors of 12. Since we know that has order 12, it suffices to check 1, 2, 3, 4, 6, 12. That does simplify things a bit, doesn't it? Not a lot, though. Let's see here. So we got 3. And is 3, is that in K again? I don't think that K time, I don't think this is in. Oh, but that's a good step to make though. That's K. You say a to the 4th, b cubed. Okay. So what's 4 is a possibility, right? I mean, it's possible. It may not be the actual one, but in principle, it's a divisor of 12. So, but you're saying it's not actually. So that's going to give me a to the 4th, b to the 4th. Is that right? No. It should give me a to the 4th times b times this one. So that's actually k, a to the 8th, b to the 4th, if you like that.
Which is K1. I don't know if that matters.
Yeah, because a is alternating between 4 and 8.
I don't think that's in k though, is it? Because
No, it's not, but that means that in order for it to be in K, it has to be either a to the 4th, b to the 6th, or a to the 8th, b to the 12th.
what happens when we get to k, a to the 4th, b to the 6th power? See, we can get that. We don't have to actually, I mean, there's various ways to do it. Here's like one way. Maybe it's good to just do it. You know what? I think in order to not compound errors, the smarter way to calculate here is independently. Because it's not that much arithmetic to do 24 and b6 and then just reduce appropriately, you know? Because the order of A is 8 and the order of B is 12. So, you know, this is k times 1 b cubed squared, right? Is that not in K? Oh. So unless we've made an error, that would seem to force then the order of this is actually 12. Yeah. Huh.
But is
Interesting.
when we multiply, or when we multiply it to the 12th, or when we put it to the 12th power, is that in K?
Oh yeah, when we put it to the 12th power, the representative powers to 1, 1.
Right. Oh, right.
Yeah.
In K. Sure.
So if I haven't made a mistake, which is okay, you guys say no, okay, great, good, then. So then we can jump ahead. So that implies then, using problem 9, that the order of k, a to the 4th b, is equal to 12.
So I just checked in the back. It says that 12 is right, so that's good.
Oh. Wait, there's answers in the back?
No,
It just says A 12.
Oh,
there aren't solutions, there aren't.
well, there are answers in the back. Okay. I'm trying to think intuitively, what does that mean? Like, how would it end up being the case that the order of the coset was less than the order of the representative? How would that happen? If at some point you pick up like a power of the representative, which is in K, right? So if none of the powers of the representative, except for of course the ultimate power, right? The order of the element, when that gets back to 1, 1, that's in K. That has to happen, right? By the time you get to the order of the element in G, the representative must also go to the identity. But if all the powers of the representatives are not found in K, that means that the order of the element in the quotient is the same as the order of the element. The order of the element in the quotient is the order of its representative in G. And this illustrates that, although somewhat clumsily. This one should work out easier, I hope. Let's see here. So we're supposed to look at k a squared b in the new k, which is this one, right? Okay. So let's square this thing. What do we get? A to the 4th b squared, right? Is that in K? Okay. So then, what? So the order is 24. We got more to worry about, don't we? Because we got ways to go here, don't we? So K a squared b. I was thinking it was easier than the other one. I'm obviously wrong. It's worse, isn't it? It's worse. So this is k a to the 6th b cubed. I mean, there might be a smarter way to do this problem than what I'm doing, but this is what I'd start with. And search for. Is that in K? What is in K, by the way? What am I looking for?
For the power of these, well,
1, 1, yeah. AB squared. A squared b to the 4th. A cubed b to the 6th.
So it's A, B, and B.
Wait, I can't do math for this. The first one adds 1. The second one adds 2, right?
yeah.
The second one is B is double the power of
What I do? Is there something wrong here?
A. No, that's right.
Okay, you guys are weirding me out. 0, and so forth and so on. So generically, what was your point? Generically, it's like n and b to the 2n.
Well, no, because when you get to, well, I guess, yeah, it still is.
Yeah.
So it's just like when you get b to the 12th, then it'll go like
Oh, eventually
b
you.
to the 6th,
Yeah.
and then 1, and
See, that's the
then you
thing.
circle back
For
around.
n not divisible by, well, I guess, divisible by 8. Oh, yeah.
Yeah, so what happens there?
There's more.
Yeah, we should worry about that.
There's a lot.
That means we could be missing things, right?
Yes.
Like you're saying something's not in K. Are you really sure it's not in K?
Well,
What? So it's like A7, B2.
Let's get to the interesting case, which would be, we get to A8, isn't it, right? Which is 1.
it'd be 8 to the 6th, 1.
1b, what is it? B to the 8, 16, which is 4. And then you get what? A, b to the 6th, right? A squared, b to the 8th, a cubed, b to the 10th. So are we sure that those are not in K?
Well, b can never be odd, though. The power of b can never be odd.
So I'd say
Very good.
the
So
next
the
time
second
it
one
goes
is
to
then,
them.
but the first one,
So test even divisors of 24. That might be easier. 2, 4, 6, 12. 4, 6, 12.
So if you think 4 might work?
4 might work. 6
Oh, yeah. It's 1 beta.
Oh, and
yeah.
and that is, as we have learned, by carefully thinking about what K is equal to K again. So the order of this element is actually 4 in the factor group. I mean, it's a little bit complicated what K is, right? I mean, K is equal to, in this case, it's A to the J, B to the 2J, right? But
2J is mod 12.
such that J is an element of Z, and yeah, exactly. The J is mod 12, right? Mod 12? It's mod 12? It's mod 12.
Well, for the B it is. Yeah. Mod
Yeah, you're fighting different modulus and different components, and so to carefully think about what those actually, what possibilities that actually.
Are we sure that like a to the 4th b squared is not in K?
That's a good. I mean, that's a good question. Is a to the 4th b squared not in K? I mean, a to the 4th. So we have to do what? We have to solve a to the 4th equal to a to the j, right? And we have to solve b squared equal to b to the j, right? 2j. 2j, right?
But it's not,
Has to be simultaneous j.
but that form doesn't fit A, B to the 6, which we established with K.
A, b to the 6th.
Like, there are a bunch of things we listed that were past 1 B to the 4th that are in K.
Let's see here. So this is
That's true,
So
yeah.
if we're thinking,
this means 4
We
is
don't double it anymore.
this means 4 is congruent to j mod what?
Mod 8.
Mod 8, yeah. And this means that 2 is congruent to 2j mod what? Okay, so how do you solve these problems?
That's a good question.
4,
Right, this is a Chinese remainder problem.
What's the check?
It's back in chapter 0.
Chapter 0?
Yeah. Or possibly chapter 1.
It's chapter 1.
Oh, it was?
Yeah.
It's just like mentioned as
Not one of those 2%.
But anyway, I don't really want to get into that at the moment. So, I mean, our way of solving this is rather ad hoc at the moment, right? I mean,
So are we saying the order's 4?
at most 4. Unless it's 2. Pretty sure it's not 1. Right? Like, I do not think that, but I mean, that's open.
So the power of b can't be odd.
Okay. You cannot get, yeah, right, you can't get B.
So it's either
Yeah.
2 or 4, for sure.
It's either 2 or 4 for sure, yeah. The question for 2, again, is can you solve this pair of congruences?
I guess you could just list out like all 24 elements then.
I would personally, I would pick on this one. You know, it's easy enough to like case-wise beat this to death if you don't remember Chinese remaindering right offhand. J equals 0, does it work? No. 0's out because 4 is not congruent to 0 mod 8. Right? In fact, what are the mod 8, what are the solutions to that?
So we can start with 4 and keep adding 8.
We could either get 4 or 12, which is 4 again, right? Yeah. Oh, I see your point though. Or 12, or I need to think about it for this one. Yeah. 20. Is that enough? I mean, I don't know. Might be enough, I guess. Down mod 12, do any of those work? I mean, if I put 4, I get 2 congruent to 8? No. If I put 12, 2 congruent to 0, that's not good. If I put 20, I get 2 congruent to 40. Still hard to manage mod 12. So I think if you just start sorting through possibilities here and you're careful about it, you can see that there's no solutions. But Chinese remainder, I think, well, this is unpleasant. Chinese remainder is most friendly for relatively prime moduli.
Yeah.
That's not what we're dealing with. Yeah.
Let's try and solve it with Chinese remainder here.
Yeah, you need to use the grown-up Chinese remaindering for not relatively prime moduli, which I don't remember off the top of my head. Of course, you can solve it by substitution. I mean, you say, okay, what does it mean to have a solution to that mod 8? It means that J
J equals 4 minus 8n.
right, and then you plug that into the other one, and just by elimination, essentially, at the level of definitions. But yeah. So I think we got it's 4. I'm relatively confident the order is 4. But now here's a question: Is there a better way to do this problem?
I'd say so.
Hope so.
But was the point of this problem for us to learn how to calculate in the direct product and to like better appreciate orders and things? Probably that's the point. So, or just for suffering. I mean, I don't know. Other question. Let's free me from this question, please. Ask me something very abstract, please. What's that?
2.10 number 1.
2.10 number 1. Ah, that does look fun. So here. Oh yeah, I like this one. This one looks like so much more fun. Thank you. Yeah, you freed me from number theory nonsense. All right. I mean, this to me feels like number theory. Anyway. Number 1 of section 2.10. All right, what do we got? We've got G is 2 by 2 matrices of the form A, B, 0, C. What are the terms and conditions here? A, B, C real numbers. Surely there's other things. Oh, A and C both non-zero. All right. And we're going to let K equal to matrices of the form 1, B, 0, 1. And I'm guessing that B is just a real number. All right. These are subgroups of GLN, well, GL2R, right? Can you see that? It's pretty clear that the conditions which are given give us non-zero determinant. So, and then you need to, of course, check. That shows that they're in there, and you can check closure under product and inversion fairly simply for these groups. But maybe that's not the point here. Show that K is a normal subgroup of G by exhibiting K as the kernel of a group homomorphism. He says, okay, so show that K is a normal subgroup of G, all right, by showing K is equal to the kernel of some group homomorphism alpha, where alpha is some homomorphism from where? From G to non-zero reals, Cartesian product non-zero reals. So if we can come up with this map that's a homomorphism, that saves us the trouble of proving that K is a subgroup, by the way. You know, the fact that it's the kernel of a homomorphism makes it a subgroup and in fact makes it normal. I suppose it's still on us to prove that G is a group, I mean, technically speaking. And in fact, going through the details of why G is a subgroup might actually give you insight as to how to construct this homomorphism. That's my suspicion. Let's try. What happens? Why is G closed? What's that look like? A, B, 0, C. Let's say A prime, B prime, 0, C prime, for lack of imagination. What happens when we multiply? We get AA prime, 0. We got A B prime plus BC prime. And then down here we got what? CC prime, yeah. Check it out. If I make this equal to 1, B, 0, 1, you know? That would mean, that's just a creative leap, guys. But my point is that if I think of it like that, then I see that I can start to see the mapping that I want, because I want that. Yeah, so what's my map? So I want alpha of, what's my G, A, B, 0, C, right? And it's got to be a pair of real numbers, and I want the kernel of, A, B, 0, C, right, to equal to what? It's equal to 1, B, 0, 1, such that B is an element of the, reals. I'm sorry, did I say kernel of that? I'm an idiot. Kernel of what? Alpha. Yeah. Kernel of the element. Idiot. Mm-hmm.
We don't really care what B is.
Mm-hmm.
It's just that A has to be its own inverse, and C has to be its own inverse.
Right. But I want this to come from the condition that alpha of A, B, 0, C, whatever this formula is, to be, right?
So the Cartesian product is our identity like 0, 0, or
Hmm.
1, 1.
The formula should somehow depend on the element in G, right?
It's non-zero.
Right. I mean, if you believe in the existence of this alpha, there's really only one thing you can do. Okay, 2. Fill in the blanks. You guys are you're thinking way too hard.
AB prime plus BC.
It's still too hard. Still, there's no primes. Yeah, you guys are killing me. How about we just A, C, right? Because then what happens if we put that? Oh, I'm sorry. I see why you're confused now. Maybe I'm wrong. Oh, maybe you guys. Maybe I'm the one that's crazy. So I want this to be. This should be. What should it be? It should be 1, 1, right?
Oh, okay. So yeah.
I mean, if
Or 1, -1, or -1.
the point here is the kernel of alpha should be formed by matrices which map to 1, 1. That's the identity in R star cross R star. Does this formula still make sense, though?
Because you don't care about it.
See, if I set this equal to 1, 1, what's that say? That says that we got that. It remains to show that that's a homomorphism, I suppose. But that's already essentially the content of me starting to fiddle with the proof that G is a group. There's a larger point here to be made that to find an isomorphism for some problem, if you don't know what it is about, you just need to get your hands dirty and like play with a group for a minute or two, like find out what it is, calculate a little bit, get a sense of what's going on. Don't just stare at it and try to write a map down. That doesn't usually work for most people. Now you can argue after the fact that by process of logical elimination, that had to be the formula, because I need a pair of non-zero numbers based on that matrix. There's only 2 non-zero entries in the matrix. It must have been those. But, we could also do other things, like it could have been the product of them, and then the other one could have been the quotient of them. And, there's all kinds of other things you could do with non-zero numbers to create new non-zero numbers. But this is by far the most elementary thing you could thought of doing with this data. And a lot of times it is the simplest thing. But I can't see that personally without just doing a little bit of calculation in the group, trying to get a sense of what I'm trying to do. And also freeing my mind of stupidity, like writing 1, 0, 0, 1 here, right? Because that'll stop you dead in your tracks, because that's just not right. The kernel is the set of elements in the domain which map to the identity in the range, or the codomain. Other questions? The example from class that I did not do. I'm going to do this. It's going to make us feel better about our day. So I'm leaving you guys the I mean, there's still more to do for that problem, right? Depending on whether or not you viewed, if you viewed that the G was a group was given, then you don't have to prove that. You can say, okay, it's a group, you know? If you don't think that that's given, then there's something to show there. But this is example 5 of section 2.9, which I think is a way easier version of the problem we were suffering with. So this is G equals 2. It'd be funny if we worked this and it gives us an insight as to how we should have worked the other problem, wouldn't it? Order of A is 18. K equals A to the 6th. We're supposed to find order of K A to the 5th in the quotient. So the solution I have looks like this. First of all, I calculate K. Ooh, yeah, see, that step hurts for our example earlier, doesn't it? Yeah. Thus, of course, G by K, what's the size of it? How big is the coset group? It is, yeah, size 6, 18 over 3. It's got 6 cosets. So therefore, what's the order of K? Ooh, were we using that? Were we using, we were thinking about the order of the element of the, we're thinking about the order of the, we were thinking about the order of the element as it relates to the order of the representative. We weren't thinking about the order of the element as it relates to the order of the factor group. That might have given us something different. I don't know. So here we have K to the 5th. So what are the possible, if this is an element of that group, right? This group has order 6, which means the order of this must be a positive divisor of 6. It's either going to be 1, 2, 3, or 6. Obviously 1 is out, right? And so you can calculate, then it's then it's basically just brute force. K to the 5th is not equal to K because A to the 5th is not in K, right? And Ka to the 5th squared is Ka to the 10th, which is again not equal to K because A to the 10th is not in K, right? And then we got Ka to the 5th cubed, which gives us what? Ka to the 15th, which is again not in K. So by process of elimination, it must be order 6.
This is more similar to the one we did in the mission 2, where you can just reference K and look at the elements in there.
Yeah, that problem we worked earlier today was harder. I'll save that one for the final. Solution, ooh, but maybe this is good. There's a second solution to this, which is that G is oh, I'm not sure we were using this enough, guys. So G is generated by A, and it's also generated by A to the 5th, right? Which means that G mod K is generated by Ka to the 5th, by the, if we have a generator for the group, we also get a generator for the quotient group by using the generator, the representative of the generator theorem, which is pretty slick. Then that immediately gives you that the order is 6 because it's a generator for a group of order 6. That might have been useful for, we should have been able to see that. I wish we still had it up here. Maybe we could see one of those was we thought one of those had order. What was it? 12, was it?
Oh, the first one, we thought 12.
We thought, do we keep thinking 12?
Yeah.
we might be able to apply this second argument to that one to show that it's a generator for that subgroup. Because the subgroup had order 12, wasn't it? Did the factor group have order 12? Okay, so the coset, the
Those had order 4. Those had order 4. The set.
you're talking about part A, part B?
Part
A.
Part A. The size of K was
A, K was 4.
K was 4 big, which means the factor group was order 24. Because there's 96 total, so 96 divided by 4 is 24. So yeah, then,
So that one would.
yeah, that would not have been a generator for the factor group. We need an element of order 24 to get a generator for the factor group. Yeah. Anyway, I digress. I'm not even sure that that factor group is it cyclic? I don't think, was G a cyclic group there?
Yeah. Well,
That was the
it
problem.
was the Cartesian product of two cyclic groups.
And that's going to be cyclic if and only if the order of those products are, and they were not. So irrelevant. Yeah. Sorry. This is cyclic technology, right? Be careful not to try to apply that where it doesn't. Don't be like me. All right, I shut up.